Alright, this is lesson 1.11 for our Pre-Calc 11 class. Unit 1 is called Radicals and Rational Exponents. Lesson 11 is called Imaginary Numbers. What we're going to learn in this lesson are what are imaginary numbers and how do we simplify radical expressions with negative values, which kind of gives away the first target. Let's see here. Okay, so first let's think about, kind of prime our brains to think about this. Complete the table. We've completed it in class. Notice that any negative 1 to the power of an odd power is negative 1. Any negative 1 to the power of an even number is positive 1. Okay, now take that idea and then consider, if we look at roots, we can get roots, negative roots, of odd numbered roots only up to this point. So for example, square root means we're looking for something multiplied by itself to come out of the radical. In other words, a perfect square. But if I take the square root of negative 1, there's no number times itself that equals a negative. So this isn't going to work. However, third root, you're looking for 3 of a kind. Negative 1 times negative 1 is positive, times the third negative makes it back to being negative. So I can find 3 of a kind in negative 1. So we could say the third root of negative 1 is just negative 1. And then the fourth root of negative 1 would be like the square root. There's an even number of negative 1s, so you can't get a negative out of that. Just like in this example, negative 1 to the power 4 is positive 1. There's no way to get 4 numbers multiplied that equals a negative. But the fifth root is an odd number of negative 1s. An odd number of negative 1s does equal negative 1. So we can do the fifth root of negative 1, it's just negative 1. And we can keep going back and forth with odd and even roots and have this pattern continued. What we're going to talk about today is what about the even numbered roots and how to find an answer that makes sense for those. So, so to answer that question, let's go back to our first definition of square roots. The square root means the square root of a number means you have a square with an area of that number, and the square root of that area would be equal to the side length of the square. So if we have a square root of 1, we're saying you have a square with an area of 1, and its side length would be the square root of 1, which is just in this case 1. If we apply that geometric definition to the square root of negative 1, we're saying basically what is the side length of a square with an area of negative 1. And when you consider area is side length times itself, or side times side, it doesn't make sense. Because a negative times a negative is a positive, and a positive times a positive is a positive. In other words, you can't draw this square. You cannot draw a square that has an area of negative 1. And all you defiant, rebellious students are just going to go try drawing one now. Don't hurt yourselves. It's not worth it. Anyways, so we're going to talk about how do we take a square root of a negative 1. This problem predates us. In fact, it goes back to a couple thousand years ago. So let's take a history through a bunch of old dead white people, men, and talk about it. First century, the idea was proposed. Let's imagine a number that would equal the square root of negative 1. Let's say we can create this number. And so that the idea was born. Many hundreds of years later, we kind of get some more mathematicians revisiting the idea and then kind of defining it. Well, there are some properties we can use with this number and rules that we can work within. Even though it's an imaginary number, it's not a real number, but we can still use properties with it. And then we finally get this definition that, okay, we can say the square root of a negative 1 is equal to this imaginary number I. However, it wasn't really necessarily openly received. At first, it kind of took a while for people to gain traction. But eventually there's a German mathematician who is arguably one of the most famous mathematicians, kind of is one of the things he did was say, okay, there's actually some useful properties for this thing, and then it kind of gained some traction from there. However, it made math more complex, but also more complete at the same time. As we will learn, imaginary numbers is how we understand roots of a quadratic when they don't have a x-intercept. It's useful in real life. If you Google it, you'll learn about like electromagnetic waves and stuff like that operate with language like volts and current and resistance, and the relationship between a lot of those variables can be modeled using expressions with imaginary numbers, I, in them, which is interesting. But anyways, so we're going to talk about I. And our basic definition that old Italian guy talked about was that the square root of -1 is I. And from that we can develop a lot of other corollaries. For example, if I square I, it equals -1. Because if I is equal to the square root of -1, I squared would be the square root of -1 times the square root of -1, which is just -1. Anyways, we could do stuff like that. If we're going to simplify some problems, the square root of -8 is very similar to the square root of 8. We could break it down to be the square root of -1 times the square root of 8. We know that the square root of 8 is 2 root 2. And we now know that the square root of -1 we can model or represent as I. So it'd be I times 2 root 2. And then the standard way to write that would be the numbers outside the root, and the letters outside the root, and the square root, and the numbers and letter bases. So we would say 2I root 2, or 2 times I times the square root of 2. The square root of -3, the square root of 3 is not simplifiable, so we can break this up to be the square root of -1 times the square root of 3, and the square root of 1 would be I, so I root 3. Another way to say that would be to take the negative out of the root as an I. Boom. And we can do 2 more examples that are similar to that. Go ahead and check those out. Make sure they make sense to you. Alright, so the bottom 4 examples are all third roots. As we said in the beginning, the third root of -1 is -1. So there's not going to be any i's coming out of a third root. So if we take the third root of -8, we could think of it as the third root of -1 times the third root of 8. The third root of -1 is just -1, and the third root of 8 is just 2. Multiply those together, we get a fully simplified answer of -2. Or -2 times -2 times -2 is -8. So the third root of -8 would be -2. Go ahead and take a moment, make sure the other examples make sense to you, and then we'll move on. So if you want to watch these examples, go ahead and pause the video, because we're going to move on. Alright, let's play with I. If I take I and I square it, it's -1. We just talked about that. If I multiply that by another I get I to the power of 3, which would be I squared, or -1, times I. -1 times I would be negative I. So I to the power of 3 is -I. I to the power of 4 would be multiplying -I by another I, which would be a -1, and then I times I is -1. So we'd have a -1 times a -1, that would be a +1. I to the power of 5 would be taking that 1 and multiplying it by another I. 1 times I is I. Take I to the power of 6 is one more I multiplied. I times I is -1, which brings us back to where we started. And I know if I keep multiplying by additional i's, I'm going to go on the same pattern. -1 times I is I times I is +1 times I is I times I is back to -1. So we can continue this pattern for all these powers of I. Notice every multiple of 4 is just 1. I to the power of 4 is 1, I to the power of 8 is 1, I to the power of 12 is 1, I to the power of 16 would be 1. And so if you know the pattern, and you know your divisibles by 4, you can just count how many beyond that pattern we are, determine if it's 1i, -1, or -I. When are you going to use this? Maybe on a quiz, probably not. The point, though, of this exercise is that we can kind of get familiar with I a little bit more. So it's a useful exercise in that end. Okay, some problems in your homework set. If I have expressions to simplify that have a bunch of radical terms, and some of those terms are negative radicands, we can simplify the radicals and collect like terms. Like terms have the same letters and the same roots. So in this case, we have I root 7s, and we have 5I root 7. And so that would be 1 plus 5 I root 7s, or 6 I root 7s. And then, of course, plus 3 plus 5 would be 8 plus 6I root 7. The next one, we can do the same thing. Simplify the radicals. We have a I root 5 on 2 different terms, so we can collect those like terms. And then we have 2 number terms we can collect. So again, take a moment, pause the video, make sure these examples make sense, because we're going to move on. Alright, so this is multiplying with radicals. First thing we're going to do before multiplying is simplify the radicals. So the square root of -49 would be 7i. Square root of 4 is 2. So really we're doing 21i times -4. Well, that's just multiplication, so no distribution. 21 times -4 is -84. So this is going to be -84i. Example D has binomials being multiplied. So we're going to do our box method. I know I times I is -1. So 9i times 4i would be 9 times 4 times -1. The 2 i's multiplied become -1. And so we can simplify that. It's going to be -36. After that, we add up the pieces in the box. We have like terms with i's. We have numerical terms that are like terms. So we'll have -22 plus 46i as our final answer. Alright, we now know about imaginary numbers, and we're pretty much done with rational exponents. This unit has talked about rational exponents, as in like exponents that have fractions as an exponent. It talked about what if the exponent's negative, and now with imaginary numbers, we've talked about what if the base is negative. And one side note, imaginary numbers are also called, or in a category called complex numbers. Fun fact. Anyways, we've also talked about how to evaluate expressions that have negative radicands, or a negative number or expression inside of a radical sign. Don't forget to take blue notes, and good luck with your homework.